Hello, my name is Thomas. I'm the team lead for UT Dallas in Raytheon's autonomous vehicle competition. In this video, we want to go over what this year's challenge, Mission Full Send, entails, our engineering process in designing a solution, and a breakdown of what our solution actually is. On the screen right now is a more technical overview of some of our vehicles. Feel free to take a closer look and pause. In Mission Full Send, we were challenged to design two autonomous vehicles that can identify a marker and deliver a payload. Our solution consists of an aerial scout drone and a ground delivery rover. I'll leave it to some of my teammates to introduce you to these designs, but in the meantime, thank you for watching and enjoy.
The Scout drone is equipped with a camera powered by OpenCV2 libraries, an RTK GPS sensor for precise positioning, and an ESP32 module to transmit the target location to the delivery vehicle. Since the competition area is flat and square, we implemented a snaking search algorithm. The drone systematically snakes across the field, applying an offset with each pass. Once it identifies the target Aruco marker, it initiates a homing sequence. The GPS coordinates of the marker are then transmitted to the delivery vehicle, and the drone returns to its launch point.
The delivery vehicle is a ground rover equipped with an RTK GPS sensor for tracking positioning and an ESP32 for receiving target location from the drone. We use a servo-controlled ramp attached to the top of the rover to deliver the payload. The ground vehicle uses a skid steering configuration with tank treads for movement. The motors are controlled by an autopilot board, specifically a QPilot Orange, that receives instruction from our secondary computer, a Raspberry Pi 4B. The frame of the rover was kept from previous year's competition, and if time and budget permitted, we would have preferred a suspension system with larger wheels. Despite that, a majority of the design choices were made with simplicity and future development in mind. The drop-off mechanism only has one mechanical point of failure compared to other payload systems and can be easily built upon or removed by the future teams. The autopilot system with a Raspberry Pi is a bit expensive, but is more powerful and flexible than using something cheaper like an Arduino, and should give future teams a huge advantage in writing scripts for future missions.
The communication system for our project involves four major components: one Jetson Nano, two ESP32s, and one Raspberry Pi. Once the camera system identifies the Aruco marker, the GPS coordinate is found through the GPS system on the aerial drone. From there, the Jetson Nano on the aerial drone communicates this location serially to an ESP32 connected through USB. This ESP32 on the aerial drone is set up as a server. This coordinate is then communicated to a client ESP32 that is connected to the ground vehicle using the ESP-NOW Wi-Fi protocol. From there, the coordinate is passed on serially to the Raspberry Pi on the ground vehicle from the client ESP32. Finally, using functions on the Raspberry Pi, the QPilot takes this coordinate and advances the ground vehicle to the GPS coordinate corresponding to the location of the Aruco marker found by the aerial drone.
All of that more or less summarizes the major hardware and software related key points in our design. I want to reiterate one more time the main discriminators that set our solution apart from our competitors. When considering a search and deploy mission like this competition, you generally don't want to invest a lot of resources in your deployment vehicle, mostly because it's susceptible to damage in the field. That's one of the biggest strengths in our solution, is how cheap and replaceable a ground rover is. It sits at half the cost of our drone with significantly less parts and a very simple 3D printable delivery system. On the contrary, our drone is powerful enough to perform most calculations and decisions, not only for the drone itself, but the rover as well. We chose to do this in such a way so we could run multiprocessing and Python on the drone, allowing for it to multitask freely, even in the case of a hardware-related failure in the camera or some bug in the software. Some other strengths include the scalability of our search algorithm to a larger size area, the pinpoint accuracy of our GPS using RTK sensors, and our robust communication protocol, including its error handling and whatnot. All of these qualities make our design a contender for one of the top teams, in my opinion, and I'm extremely proud of everyone on our end for their support and hard work. Thank you all for watching, and bye-bye now.